Alright, welcome to lab number 2, motion of a falling object. Here's our table of contents, which you can read. So we're going to start off with our introduction and initial conditions. Our lab purpose is to show how concepts of gravity and drag affect falling objects and their positions and such. So our initial conditions are that a force applied by our hand and the force of gravity applied by the ball and its mass equal and opposite to Newton's law of reciprocity, and as we drop the ball, its surroundings will exert drag on it upwards, and gravitational force will exert force on it downwards. But our first computational model doesn't really work with that. The other very important thing about our initial conditions and introduction is that our unit vector is going to be 0, -1, 0, because we're really only moving in the y direction. Technically it's moving in the x and z direction, but it's so small that messing with it would just be negligible and a waste of time. So, equations. These first two are from lab number 1, just Newton's second law being used as the velocity update formula and the position update formula. These are both well known. Then we have our two new ones. Our force of gravity is our gravitational constant times the two masses times each other times the radius between them squared times our r hat for just directional purposes. However, on Earth, since our height above the radius is so negligible, we just end up calculating that the force of gravity on Earth is just the gravitational constant times the mass of Earth times the radius of Earth squared, which is 9.8, which is g, which we're pretty familiar with. So we approximate our force of gravity to be equivalent to mg. Our force of drag is a little different. We have our proportionality constant for b, which you calculate using a variety of methods, but in our case we're doing trial and error, times our velocity squared, which is just the drag model we were instructed to do in the lab. So with our data, this is the tracker video of our falling object. I chose a paper ball because it had a relatively high amount of surface area and it would cause more drag. So you can see our our t and y model over here, which you could plot it into this chart of position versus time, which is a relatively negative exponential graph. As for understanding the code, we can see that some important things are mattering here. Most importantly, on this side is g is equivalent to 9.8, which we discussed with this formula, and that our velocity update formula is taking in velocity plus force of gravity over ball mass, which is our F net, because our F net is only being impacted by gravity in this initial model. So our F grav is 0 negative ball m times g, which is exactly what it is right here. We plug that velocity into the position update formula, and we're left with this. This is our data from that computational model, and we can see it's almost a perfect exponential decrease. Now, we can see if we compare the two models against each other, there's a couple of noticeable differences. First of all, we can notice that the position from the computational model is far lower in altitude compared to the observed data, which means that there must be some force slowing the observed data down that we didn't compute with this model. That is, of course, drag, which we computate with our second model. So in this one, instead of having b being 0, we have b equivalent to something, a number 0.369, which we've gathered through trial and error when our position would line up with our computational model from the observed model. Then we just add that to our F net, which we'd plug back into velocity and position, because our net force is now going to be gravity plus our drag, and since gravity is negative in our axes, they're just going to be your force of drag minus your force of gravity times your position, times your position vector. So, with that in mind, we're left with this. This is all our data. We compute the 3. Now, a couple of noticeable things about this. We notice that our in position of the drag model and our observed are almost identical, meaning that it's likely drag impacting this observed position. But there's a couple of errors present. First of all, it's likely that there weren't enough tracker dots to accurately measure position and compare it to these two models efficiently. And also, because the position is of a lower altitude here, below both the graphs at all points, that likely means that the ball started with this sort of initial velocity downwards, causing it to reach a lower altitude quicker in comparison to these. That is the main two errors that I noticed present. Summary questions. Which models, if any, predicted terminal velocity? Well, the only one that has something subtracting from the gravitational force. So as this formula, you can see that our net force is equivalent to our gravity plus our drag. If we're going to have a delta V equivalent to 0, we have to have our net force to be 0, meaning that these two have to cancel out. The only way these two cancel out is if they're both present, which means our computed model with drag is the only one that would be able to work. If there wasn't a force drag, this thing would just accelerate down infinitely and constantly increasing in speed. And our second question is, if the object was initially thrown down, would the terminal velocity in this case be the same or different from the case in which it was initially dropped from rest? So if we go back to this formula, we can notice that since this just takes in v squared, causing it to increase to a level higher than the initial velocity, what would end up happening is that your force net would be uneven, which means that these two forces, force of gravity and force of drag, would cancel out inherently. So what would end up happening is that terminal velocity would not change numerically, but it would be reached in a lot less time because you'd be giving it a bit of a boost. Thank you so much for watching, and that's all I have.